There's something out there that shouldn't exist. Not in the way we understand comets, not in the way we've catalogued thousands of icy visitors from the depths of space. Its name is 3I Atlas, and on October 14th, 2025, after months of careful observation, after stacking more than 9,000 individual photographs taken by one of humanity's most sensitive instruments, astronomers discovered something that makes the silence louder than any announcement could be. They found nothing. Not nothing in the sense of emptiness, nothing in the sense of absence. Where there should have been a tail streaming away from the sun, where there should have been a diffuse cloud of dust and gas spreading outward like breath in cold air, there was only a point of light, sharp, contained, behaving exactly like a distant star, not like a comet racing through our solar system. Picture this with me for a moment. Imagine the night sky filled with telescopes, each one worth millions, ground-based observatories with mirrors the size of houses, spacecraft floating in the silence beyond our atmosphere, all of them, hundreds of instruments, pointed at the same target, all tracking a single visitor as it moves through the inner solar system. The resources dedicated to this one object represent decades of technological development, billions in funding, thousands of hours of observation time, and what the most sensitive instrument of them all finally reported, after combining every photon it could gather, was a mystery wrapped in contradiction. Let me tell you how we got here. Let me walk you through this slowly, because the details matter. The details are where reality starts to bend. The Transiting Exoplanet Survey Satellite, TESS, wasn't built to study comets. It was designed to find planets around other stars by watching for the tiny dips in brightness when those planets pass in front of their suns. It stares at patches of sky for weeks at a time, taking image after image, building up enormous data sets that can reveal signals too faint for any single observation to catch. When astronomers pointed this instrument at 3I Atlas, they knew they were using it in an unconventional way, but they also knew that if any telescope could pull a faint structure out of the darkness, TESS could do it. The technique they used is called co-adding. Think of it like this. Imagine trying to hear a whispered conversation in a crowded room. One attempt, you catch only fragments. Noise overwhelms signal. But if you could record that same moment dozens of times, hundreds of times, thousands of times, and layer all those recordings together, the random noise would cancel itself out, while the actual words would accumulate, growing stronger with each repetition. That's what image stacking does with light. It turns whispers into statements. Over 9,000 frames, each one capturing photons that traveled millions of miles from the sun, bounced off whatever 3I Atlas is made of, and arrived at TESS's detector. Each frame added to the stack, building up sensitivity to structures so faint they'd be invisible to the naked eye. Invisible even to most professional telescopes. The signal-to-noise ratio increased dramatically with every added image. Faint features that hide in single exposures emerge from stacked data, like coastlines emerging from morning fog. And what emerged from this particular fog was a point source. The technical term carries weight because it has specific meaning. In astronomy, a point source is an object so distant or so small that even through your telescope's optics, it doesn't spread out. It remains a single point of light. Stars are point sources because they're so far away that even though they're enormous, they collapse into pixels. Galaxies billions of light years distant can appear as point sources. But comets? Comets are supposed to be different. Comets are supposed to spread out. They're supposed to show structure. The nucleus itself might be small, just a few miles across, a dirty snowball of ice and rock. But as it approaches the sun, heat causes ice to sublimate directly from solid to gas. That gas expands outward, carrying dust particles with it, creating a cloud called the coma. Solar radiation and the solar wind push on this material, shaping it into the iconic tail that's inspired wonder and terror for millennia. The whole structure, nucleus plus coma plus tail, can stretch for millions of miles. It should be extended. It should show up in images as something fuzzy, something that fades gradually as you move away from the center. When TESS looked at 3I Atlas, it saw none of that. The team measured what's called a radial brightness profile. This is exactly what it sounds like, how the brightness changes as you move outward from the center of the object. For a star, for a true point source, the brightness drops off in a very specific way, determined by your telescope's optics. Every telescope has what's called a point spread function, a PSF, which is the pattern of light you get from a point source after it passes through your mirrors or lenses. It's like a fingerprint, unique to each instrument. When you point your telescope at a star and measure how the light spreads out in your detector, that pattern is your PSF. TESS looked at 3I Atlas and saw only its own fingerprint, nothing beyond it. No extended glow, no subtle brightening that would indicate dust or gas spreading outward. The radial profile dropped exactly like a star's profile, not like a comet's. The analysis team could quantify what this meant. They could derive constraints on dust density, on particle size, on ejection velocity, all the parameters that describe how material leaves a comet and spreads into space. And all those numbers pointed toward the same conclusion. Whatever dust might be present around this object, if any exists at all, it's not behaving the way comet dust behaves. It's not creating the extended structure that thousands of previous comet observations have shown us to expect. Now, here's where the story starts to split, because other observations tell a different tale. And this is where things get strange, in a way that feels less like scientific uncertainty and more like fundamental disagreement about what reality is doing. The James Webb Space Telescope, JWST, that $10 billion jewel of infrared astronomy, turned its mirrors toward 3I Atlas. The observations came back clear. Carbon dioxide, water vapor, a gas coma rich in volatiles. The spectrographs picked up molecular signatures, emission lines that tell us atoms are being excited, molecules are vibrating, gases are flowing outward from whatever lies at the center. These aren't ambiguous signals. These are the chemical fingerprints of active sublimation, of a comet doing exactly what comets do when the sun's heat reaches them. Another mission, SphereX, operating in infrared wavelengths, reported large amounts of vaporized carbon dioxide around 3I Atlas. The carbon dioxide to water ratio was unusual, even by the standards of weird comets. But it was there, measurable, real. So we have this situation, one instrument stacking thousands of optical images with extraordinary sensitivity, says there's no extended structure, no dust cloud, no tail, just a point. Meanwhile, other instruments, tuned to infrared wavelengths, are screaming that something is definitely happening. Gas is pouring off this object. Volatiles are escaping into space. Chemical signatures of vigorous activity are undeniable. You're forced into a corner here. Either the coma is so compact, so unnaturally dense and confined, that it remains invisible to optical telescopes while still producing detectable gas signatures, or something else entirely is happening. Something that doesn't fit our models of how icy bodies behave when the sun warms them. It's like watching a campfire burn and seeing no smoke rise. You can feel the heat. You can measure the combustion products in the air. but there's no visible smoke. Either the smoke is being compressed into invisibility by some mechanism we don't understand, or what we're calling a fire isn't really a fire at all. The contradiction sits there, unavoidable. TESS spent months staring at this object with one of the most sensitive instruments we've ever built for detecting faint, extended structures. It saw nothing. But other instruments, measuring different wavelengths, different physical processes, detected clear evidence of activity. One of these observations is missing something crucial, or our entire framework for understanding what a comet should look like is about to break. Let me explain why this matters more than you might think. We've seen comets do strange things before. We've watched them brighten unexpectedly, split into fragments, survive passages so close to the sun they should have vaporized. But we've never seen them do this. We've never had an object that so perfectly mimics a point source in optical wavelengths, while simultaneously showing chemical signatures of vigorous activity in infrared. The numbers don't just fail to add up. They actively contradict each other. This isn't a minor discrepancy that can be explained by different observing conditions or instrumental quirks. This is a fundamental disagreement about what the object is doing. And here's what keeps people up at night. The scientists who spend their careers studying these visitors from beyond. The TESS data is public now. Anyone can download it. Anyone with the right software and knowledge can run their own analysis, check the numbers, verify the processing. The no-tail finding is solid. It's reproducible, which means we need to figure out what's happening. Because if we can't explain this with conventional comet physics, we're going to have to start considering explanations that sound uncomfortably exotic. But before we travel down that path, we need to understand just how deep these contradictions go. Why different instruments are painting completely different pictures of the same object. What it means when reality appears to depend on how you look at it. Picture JWST swiveling its golden mirrors toward 3i Atlas. Those mirrors, kept at temperatures just above absolute zero, are exquisitely sensitive to infrared light. This is light with wavelengths longer than what our eyes can see. The realm where warm objects glow and where molecules emit their characteristic signatures. JWST doesn't need reflected sunlight to detect a coma. It's not looking at dust scattering. It's listening to the molecules singing in the infrared, and those songs are loud and clear. The spectrographs break light into its component wavelengths, creating a rainbow that reveals which chemicals are present. Each molecule vibrates and rotates in specific ways, absorbing and emitting light at precise wavelengths. Water vapor has its signature, carbon dioxide has another. When you see these signatures, you're not inferring chemistry, you're directly measuring it. The light itself carries the information, encoded in wavelengths that are as reliable as fingerprints at a crime scene. JWST saw those signatures around 3i/Atlas, unambiguous, confirmed by multiple observations. Optical telescopes are different instruments entirely. They're looking at reflected sunlight, at how dust particles scatter the sun's rays back toward us. To see structure in an optical image, you need extended dust. You need particles spread out over space that can catch and redirect sunlight. If the dust is too compact, too close to the nucleus, or if the particles are the wrong size to efficiently scatter at optical wavelengths, you might not see much of anything, even if gas is pouring off the object. This is where scattering functions come into play. Small dust particles, grains measured in microns, scatter light efficiently. They form the classic comet tails we see in photographs, those sweeping curves of brightness extending for millions of miles. Larger particles, millimeter to centimeter sized grains, don't scatter as well. They have more mass, so they're harder to push away from the nucleus. Solar radiation pressure that easily moves tiny grains barely budges larger ones. These bigger particles might hover close to the object, creating a compact but optically faint envelope that optical telescopes struggle to detect, even though plenty of gas is sublimating from their icy surfaces. There's also geometry to consider. The phase angle, the angle between the Sun, the object, and the observer, changes how we see any tail or coma structure. If we're looking at the object from an unfortunate angle, a tail could be foreshortened, pointing almost directly toward or away from us, rendering it effectively invisible even if it exists. Different instruments observed at different times, from different positions in their orbits, seeing the object from different angles. A tail visible to one might be hidden from another purely by geometric bad luck. We've seen cross-instrument disagreements before. They're not unprecedented. Comet ISON in 2013 was predicted to be the comet of the century, a spectacular show that would dominate the night sky. Different telescopes reported different levels of activity at different times. Eventually, it disintegrated during its close approach to the Sun, never delivering the predicted spectacle. C2017K2 showed a coma in some observations and looked quiet in others, sparking debates about whether it was truly active or just venting gas intermittently. The difference with 3I Atlas is scale. This isn't just showing variations, it's showing a binary split, either tail or no tail, either point source or extended object. There's very little middle ground in the observations. You don't get reports saying, "We see a faint tail that's somewhat smaller than expected." You get reports saying, "We see clear gas signatures," and other reports saying, "We see absolutely no extended structure." The timing mismatches make it worse. JWST observed during certain windows, ground telescopes during others. TESS was staring continuously, but at lower spatial resolution than some other instruments. What if the object is intermittently active, pulsing out dust and gas in bursts rather than steady streams? Then one telescope might catch it during an active phase, while another sees only quiescence. The observations would look contradictory, even though both are accurately reporting what they saw at that moment. Imagine a lighthouse that only turns on occasionally, unpredictably. One ship passes and sees the beam. Another ship passes hours later and sees only darkness. If those two ships later compare notes without knowing about the intermittent nature of the light, they'd think they were describing different lighthouses. That's essentially what might be happening with 3I/Atlas. Telescopes taking snapshots at different times, catching the object in different states, building up a collection of observations that don't cohere into a single coherent picture. But even accounting for all these effects, the level of disagreement is unusual. Deep stacking of optical images from professional observatories should recover faint dust features if they're there. The whole point of stacking thousands of frames is to see things that individual exposures miss. The fact that TESS, after all that work, sees nothing extended suggests either the dust is extraordinarily compact, beyond what we typically see in comets, or it's simply not there in the quantities we expect. And if it's not there, if the dust production is somehow suppressed or confined, where is all that gas coming from? Gas doesn't just appear. It comes from ice sublimating, either off dust grains or from the nucleus directly. Either process should produce dust as well. You can't have one without the other in normal comet behavior. Ice and dust are mixed together in the nucleus. When ice sublimates, it should drag dust particles along with it. That's basic physics. Unless something is separating the processes, unless the gas can escape while the dust stays trapped, unless the composition is so unusual that sublimation happens differently than we've ever observed. Unless you start to wonder if you can trust any single instrument. Each one is seeing part of the elephant, reporting faithfully what its particular senses detect. The optical telescopes report no extended dust. The infrared spectrographs report active gas emission. Both could be correct about what they're measuring, while the composite picture remains incoherent. This is where most astronomical mysteries get resolved, actually. You gather more data, refine your models, realize you were missing some subtle effect. Unexpected scattering properties get discovered. Unusual compositions get measured. The puzzle pieces eventually fit together, and what seemed contradictory reveals itself as just incomplete information. But every time we add another observation of 3I/Atlas, something strange happens. The picture gets murkier instead of clearer. More data doesn't resolve the contradictions. It amplifies them. New measurements create new questions rather than answering old ones. And now we come to what might be the most important question in this entire mystery. The observation that could actually resolve everything, or make it infinitely worse. Because there's one instrument that might have had the perfect view, the perfect resolution, the perfect geometry, to see what 3I/Atlas really looks like up close. The Psyche mission. NASA's spacecraft traveling through interplanetary space on its way to study a metal-rich asteroid. Its trajectory through the solar system, its suite of imaging instruments, capable of capturing detailed photographs. The windows, when it might have been within viewing range of 3I/Atlas. Close enough that a targeted observation could have settled this mystery. Where are those images? Do they exist? And if they exist, why haven't we seen them? The silence around this question is louder than any of the contradictions in the data. Because spacecraft don't just fly blind through space. They have cameras. They take pictures. Mission teams routinely point instruments at targets of opportunity when circumstances allow. And if Psyche captured images of 3I/Atlas during a close approach, those frames might be sitting in an archive somewhere, waiting for someone to request them, waiting for someone to ask the right questions, or waiting for reasons we don't yet understand. But let's not get ahead of ourselves. Let's not leap to conclusions that feel comfortable in their conspiratorial simplicity. Let's instead walk carefully through what we know, what we don't know, and what we could know if we look in the right places. The mystery deepens, not because we lack information, but because the information we have refuses to tell a single coherent story. And somewhere, in data that's been collected but perhaps not yet examined, in observations that were made but maybe not yet released, the truth is waiting, patient, undeniable, strange enough to change how we think about what visits us from the dark between stars. We need to talk about what might be the most important observation that hasn't been discussed publicly. An observation that could exist right now, archived somewhere in the vast databases of spacecraft telemetry and imaging data. An observation that might answer every question we've been asking about 3I/Atlas, or raise questions we're not prepared to face. NASA's Psyche spacecraft launched with a specific mission to reach and study the metallic asteroid 16 Psyche, a world thought to be the exposed core of an ancient protoplanet. But along the way, during its years-long journey through interplanetary space, Psyche carries cameras, imaging instruments designed primarily for the asteroid encounter, but capable of taking pictures during the cruise phase, during the long months of travel between Earth and destination. This is standard procedure for interplanetary missions. You have cameras, you're flying through space, you take pictures when opportunities arise. calibration images to test instrument performance, navigation frames to verify pointing accuracy, opportunistic science observations when interesting targets pass through your field of view. The spacecraft doesn't sleep. It operates continuously, and mission teams routinely capture bonus data when circumstances permit. NASA has released some of these cruise phase images publicly. Calibration shots of Earth and the Moon from various distances, star fields for navigation verification, the kinds of images that help engineers confirm systems are working properly and give them practice for the primary mission. These releases are normal, expected, part of the transparent operation of publicly funded space exploration. Here's where the timeline gets interesting. When you calculate the ephemerides, the precise positions and trajectories of both Psyche and 3I Atlas over time, using publicly available orbital data from JPL's Horizon system, you find windows, periods when the interstellar visitor would have been within potential viewing range of the spacecraft's cameras. Not necessarily close in an absolute sense. Space is vast, and distances that seem near on solar system scales are still enormous, but close enough that a targeted observation might have captured useful data. Close enough that if mission planners decided to point the cameras toward this mysterious object, they could have obtained images with resolution and clarity that Earth-based telescopes can't match. The exact geometry depends on orbital mechanics that anyone can calculate from published mission parameters. The calculations aren't secret. The possibility exists in numbers that anyone can verify. During certain windows, Psyche's position relative to 3I Atlas would have allowed for observation opportunities. Whether those opportunities were taken, whether the cameras were pointed, whether data was captured, these are different questions. Questions with answers that should be findable. NASA maintains extensive archives of raw mission data. The Planetary Data System, the PDS, is designed specifically to preserve and distribute data from planetary missions. Most missions eventually release their raw frames, or at least comprehensive metadata about what was captured and when. These archives are how amateur astronomers sometimes discover comets or asteroids lurking in old images, how researchers go back years later and find things that were missed during initial analysis. The data sits there, publicly accessible, waiting for someone to look at it from a new angle, or with a new question in mind. The raw images from Psyche's instruments should be findable. They should be catalogued in the PDS, or in mission-specific archives, organized by date, by target, by instrument configuration. The metadata should tell us what was pointed where and when. This is how the system is supposed to work. Transparency, accessibility, data collected with public funding available for public analysis. The mystery is that no public release of raw Psyche images showing 3I Atlas during closest approach periods has been announced. No mission update mentioning such observations. No data release notice indicating that frames of the interstellar visitor are available for download. The silence is notable, not because it's suspicious by itself, but because it creates an information gap that we need to understand. Let's walk through the benign explanations first. This is important, because jumping to conclusions serves no one. There are perfectly reasonable, completely non-conspiratorial explanations for why data might not be immediately available. Spacecraft data downlink is a constrained resource. This is a technical limitation, not a choice. Deep space missions communicate with Earth through NASA's Deep Space Network, a collection of enormous radio dishes spread across the globe. But there are more missions than there are antennas. Communication windows are scheduled carefully, and even during those windows, bandwidth is limited. You can only send so much data back to Earth during each contact period. Mission planners have to prioritize what gets transmitted. Engineering telemetry comes first, always, because you need to know the spacecraft is healthy. Science data from the primary mission objectives comes next. Then everything else, in order of scientific priority and available bandwidth. If Psyche's cameras captured images of 3I Atlas, those frames might be sitting in the spacecraft's memory right now, scheduled for downlink during a future communication window when bandwidth becomes available. Space missions often have backlogs of data waiting to be transmitted. It's not unusual. It's just the reality of operating at interplanetary distances. There's also data management to consider. Spacecraft don't have unlimited storage. They use what are called ring buffers, memory systems that overwrite old data when new data comes in. If Atlas images weren't flagged as high priority by the mission operations team, if they were considered secondary to primary mission preparations, those frames might have been compressed heavily to save space. Or in the worst case, they might have been overwritten by later observations as the buffer cycled through its storage capacity. This happens more often than the public realizes. Not every frame captured by a space mission makes it back to Earth in full resolution. Some data is simply lost to the practical constraints of data management in deep space. Metadata and indexing errors are another real possibility. Large archives are complex systems. Files get mislabeled, timestamps get recorded incorrectly, headers get corrupted during transmission or storage. Anyone who's worked with large astronomical databases knows how easily data can become effectively lost just by being filed in the wrong place or with the wrong keywords. An image of 3I/Atlas might be sitting in the archive right now, labeled as a calibration frame or a generic star field, waiting for someone to notice what's actually in it. The data might exist, accessible, but effectively invisible because the search terms don't match what's in the catalogue. Then there's the bureaucratic explanation, perhaps the most mundane and most likely. Space agencies have embargo periods, data rights policies, mission team exclusive access windows. These policies exist for good reasons. They protect the scientists who designed and built the instruments, giving them time to analyze their data and publish their findings before the whole world gets access. This is standard practice across science. The people who do the work get first opportunity to benefit from it. It's fair. It's reasonable. It prevents situations where mission teams spend decades developing instruments only to have other researchers scoop their discoveries using data they couldn't have collected without that development work. It might simply be that images exist. The mission team is analyzing them right now, and they'll be released on a schedule that hasn't arrived yet. Science teams often get months or even years of exclusive access before public data release. This protects careers, enables publications, and maintains the incentive structure that makes space missions possible. Nothing sinister, just the normal friction of how space science operates within institutional and professional frameworks. All of these explanations are reasonable. None of them require conspiracy or cover-up. They're just the reality of how spacecraft missions work, the technical and bureaucratic constraints that govern data collection and distribution. These are the explanations we should favor by default, because they're the most common, the most consistent with how thousands of other observations have been handled over decades of space exploration. But here's the thing. Absence of evidence is not evidence of absence. We don't know what was captured because we can't see the full archive. We don't know what was prioritized for downlink, what was compressed, what was labeled how. The metadata that would tell us these things might itself be incomplete or inaccessible to public searches. We're left with an absence that could mean many things, and without more information, we can't distinguish between them. What we can do, what we should do, is ask. Freedom of Information Act requests can compel release of government-held data. Archive access requests can be filed through proper channels. Mission logs exist. Communication schedules are documented. Instrument activity reports detail when cameras were active and what they were pointed at. These are documents that exist within NASA's institutional structure, and they can be requested through established procedures. The question isn't whether Psyche could have observed 3I Atlas. The orbital mechanics say it could have. The question is whether it did, and if it did, where are those observations now? Are they waiting in a processing queue? Are they restricted by embargo? Were they never captured in the first place? Or is there something else, some other reason we haven't seen them? This is where the story could go in multiple directions, and we need to be honest about each possibility. If the images exist and get released through normal channels, we might finally see what 3I Atlas really looks like. High-resolution views of its shape, its surface, whether it has an extended coma or appears as a compact nucleus. Those images could resolve the contradictions between TESS and JWST, showing us which instruments were seeing the complete picture and which were missing something. The mystery could end with a definitive answer. If the images don't exist, if the search of archives and mission records shows that observation windows were missed, or cameras weren't pointed, or priorities were set differently, that's valuable information too. It tells us that opportunities weren't seized, that a potentially crucial observation fell through the cracks of mission planning. It would be disappointing, but it would also inform how we advocate for future observations, how we prioritize targets of opportunity, how we think about what gets observed and what gets overlooked during the brief windows when interstellar visitors pass through our neighborhood. And if the images exist but can't be accessed, if archive searches and FOIA requests get responses that acknowledge data exists, but claim it's not available for release, then we have a different kind of problem. One that raises questions about transparency and data governance in publicly funded space science. Questions about who gets to decide what information reaches the scientific community and the public. Questions about whether the normal protections of embargo periods and mission team rights are being applied appropriately, or whether something else is influencing decisions about data access. I'm not claiming to know which scenario is real. I'm saying we need to find out. Because the architecture for finding out exists, the tools are available. We can calculate observation windows. We can search archives systematically. We can file formal requests. We can cross-reference mission logs with archived data to look for discrepancies. This is detective work, not speculation. It's following the paper trail, the digital trail, to see where it leads. And while we're examining what might be missing from our picture of 3I Atlas, we need to ask a more fundamental question. What if we've been trying to fit this object into the wrong category from the start? What if the reason our observations don't cohere is that 3I Atlas isn't what we think it is? Let's step back from archives and spacecraft for a moment. Let's look at the physical object itself and ask what else it could be if it's not a standard comet. Imagine a chunk of material from another star system, shaped by formation conditions different from anything in our solar system. Maybe it's mostly inert, not actively sublimating like a typical comet, just a large body, rock and ice mixed together, but without the vigorous activity we associate with comets passing through the inner solar system. Yet it's still releasing small amounts of gas through cracks, through rare pockets of volatile ice exposed on its surface by ancient impacts or internal stress. Micro-outgassing, enough to produce the chemical signatures JWST detects, but not enough to create the massive dust production that would form a visible tail. This would explain the gas without requiring the dust. The object stays compact, appears point-like in optical images, but still shows chemical activity when you look at the right wavelengths. The problem with this model is quantifying the gas production rates. JWST's measurements suggest significant volatile loss. You can't hide that much gas production in microcracks without also generating dust. Ice doesn't sublimate cleanly. As it vaporizes, it drags particles with it. You'd need a very specific composition, maybe pure volatile ices somehow separated from dust, and that seems geologically implausible. How would such separation occur during the formation of a body in another star system? Or consider this. What if 3I/Atlas isn't a single object at all, but a tightly bound swarm of smaller fragments, all traveling together? Each fragment individually too small to resolve even with our best telescopes, but collectively producing the brightness we measure. Think of it like a school of fish or a flock of birds, where the group behaves as a unit but is composed of many individuals. Each fragment in this swarm produces a little gas, a little dust, but the material stays confined within the swarm rather than streaming away in a classic tail. Gravitational interactions between fragments, or perhaps electrostatic forces if the fragments carry charge, keep the group coherent. To our telescopes, looking from millions of miles away, the swarm appears as a single point source because the individual fragments are closer together than our angular resolution can separate. The gas production would be distributed across many small surfaces rather than coming from one nucleus. This might create different scattering properties than we expect. Dust particles ejected by one fragment might be captured by another. The collective behavior of the swarm might suppress the tail formation we see in traditional comets. But this model has problems too. Why would fragments stay bound together over interstellar distances? They'd need some kind of collective gravitational pull. But objects small enough to remain unresolved would have negligible gravity. They'd drift apart over the millions of years it takes to travel between stars, unless some other force holds them together. And even if they somehow remain bound, a swarm should show some structural variation, some elongation or fuzziness in high-resolution images. We should see something that hints at multiple components, even if we can't resolve individuals. The TESS observations show none of that, just a point. Now we enter more exotic territory. Suppose the dust particles around 3I/Atlas are electrically charged. Not unusual by itself, ultraviolet light from the sun and cosmic rays can ionize atoms, creating charged particles. But suppose there's also a magnetic field or electric field strong enough to hold those charged particles close to the nucleus. Electromagnetic forces can trap charged particles in configurations that don't follow simple ballistic trajectories. We see this in planetary ring systems, where electromagnetic effects help confine dust. We see it in laboratory plasma experiments, where magnetic fields shape the behavior of ionized gases. We see it in astrophysical contexts, where electromagnetic forces dominate over gravity. If 3I/Atlas is somehow carrying a charge, if it's generating fields through some process, the dust might not escape into a tail at all. It might hover, circulate, remain confined in a dense envelope close to the nucleus. The gas would still escape because neutral molecules are harder to trap electromagnetically, but the dust would stay put, invisible to optical telescopes looking for extended structure because it never extends. It remains bound in a compact cloud that appears point-like even in stacked images. This would explain almost everything. the compact optical appearance, the gas detections in infrared, the missing tail. The contradiction between instruments would resolve because they're measuring different components, gas versus dust, that behave differently under electromagnetic influence. The catch, and it's a significant one, is mechanism. We have no model for how an inert, icy body generates the necessary fields. You'd need something active, something generating energy beyond simple solar heating. Comets don't have magnetic fields. Their nuclei are too small, composed of non-metallic materials. They don't have the internal structure to support dynamos like planets do, so where would the field come from? Unless it's not a natural field, unless it's generated by something engineered. And here we arrive at the hypothesis that makes scientists deeply uncomfortable, but that we have to at least acknowledge, given how strange everything has become. What if this object is artificial? What if it's engineered, carrying active systems, producing the signatures we're measuring through technological rather than geological processes? I'm not saying this is what I believe. I'm saying it's what the data is starting to whisper, what the contradictions are pointing toward when you eliminate all the conventional explanations. An artificial object could explain the contradictions perfectly. Systems generating the gas emissions without requiring ice sublimation. Active control of dust, keeping it confined electromagnetically or through other means. The compact appearance, natural for a manufactured structure, rather than anomalous for a natural body. But this is an extraordinary claim. Extraordinary claims require extraordinary evidence, and we don't have that evidence yet. We have anomalies. We have contradictions. We have unexplained observations. Those aren't proof. Those are puzzles waiting for solutions. And history teaches us that most puzzles have mundane solutions, even when they initially seem bizarre. Each of these models makes predictions, though. The micro-outgassing hypothesis predicts we should eventually see some dust production, faint but detectable, if we stack enough observations from multiple instruments. The fragment cloud model predicts structural variations over time as the swarm evolves and individual fragments shift position. The electromagnetic model predicts we should find field signatures if we look for them, polarization anomalies in scattered light, maybe radio emissions from plasma processes. And the artificial model? It predicts things that don't occur naturally, geometric structures if we achieve high enough resolution, spectral lines from industrial processes or unusual isotope ratios, temporal patterns in activity that suggest control rather than chaos, organization rather than random thermal processes, correlations across multiple wavelengths that indicate coordinated energy release. What's remarkable is that none of these models is a perfect fit. Each explains some observations while creating new questions about others. The natural explanations require unlikely compositions or configurations. The exotic natural explanations require physics we haven't observed in comets before. And the artificial explanation requires us to accept that we're looking at technology from another civilization, which is a leap that most scientists won't make without overwhelming proof. But we're going to need one of these explanations, or something even stranger we haven't thought of yet, because the standard comet model is broken for 3I Atlas. We can't keep calling it a comet while it refuses to act like one. At some point, if an object consistently violates your expectations, you have to update your model of what the object is. We might be at that point. The question becomes testable. We can define exactly what evidence would move us from natural to exotic, from exotic to artificial. What observations would force even skeptical scientists to seriously consider explanations they'd rather avoid? First, resolved structure inconsistent with known physics. If we could image 3I Atlas with resolution high enough to see its shape, and that shape showed sharp edges, right angles, symmetric patterns, or articulated components, that would be significant. Natural objects are lumpy, irregular, shaped by accretion and collisions and gravitational forces that don't produce geometric precision. A sphere isn't suspicious. Spheres minimize surface energy and form naturally. But a cube, a cylinder, components that move relative to each other, those would demand explanation beyond natural processes. Second, spectral lines from compounds that don't belong. Comets show water, carbon dioxide, carbon monoxide, organic molecules, all things we expect from primordial material formed in stellar nurseries. If spectroscopy revealed elements or compounds that only exist of products of technology, artificial isotope ratios that don't occur in nature, that would be a red flag impossible to ignore. The universe makes a limited palette of chemicals through stellar nucleosynthesis and natural chemistry. Anything outside that palette needs accounting for. Third, multiband registration anomalies. Take images in different wavelength bands and overlay them precisely. Natural objects show predictable patterns. Hot regions emit more infrared. Dust scatters optical light. Gas emits at specific wavelengths determined by atomic physics. If the images don't align the way physics says they should, if there's structure in one band that doesn't correspond to anything in others, that suggests something more complex than simple thermal and scattering processes. It suggests active systems producing different types of emission independently. Fourth, metadata and telemetry signatures. This is about data provenance. If spacecraft observations exist, the raw frames should have headers with timestamps, instrument settings, checksums, calibration data. These technical details can be verified, cross-checked against mission logs and independent observations. Inconsistencies might indicate problems with data handling, but more importantly, the presence of consistent, verifiable metadata strengthens any claim about what was observed. You can't prove something extraordinary with data you can't authenticate. The chain of custody matters as much as the observation itself. And fifth, correlated signals across different physical domains. If 3i Atlas showed simultaneous optical brightening, radio bursts, X-ray flashes, and particle detections, all time-locked to the same events, that would be remarkable. Natural processes can produce multi-wavelength emission, but the correlations follow patterns we understand from decades of observing stellar objects and high-energy phenomena. Something completely novel in its multi-wavelength behavior would demand a new explanation. Something beyond what natural astrophysical processes produce. The burden of proof for claiming artificial technology is enormous, and it should be. Science has progressed by being rigorous about evidence, by demanding reproducibility, by not accepting claims just because they're exciting, or because they fit our hopes or fears. But science has also progressed by following anomalies, by taking seriously the observations that don't fit, by being willing to update models when data demands it. We're at a moment where the 3i Atlas observations are strange enough to warrant serious attention, but not yet clear enough to draw firm conclusions. What happens next depends on whether we can access the decisive observations, whether those Psyche images exist and can be found, whether new coordinated observations can fill the gaps in our understanding, or reveal that the gaps are deeper than we thought. The framework is there. The criteria are defined. We know what evidence would be convincing. Now we wait to see if that evidence emerges from archives, from new observations, from the careful work of checking and cross-checking data against the predictions of different models. The answer is out there, somewhere in photons that have already been collected, or in observations we can still make. We just have to look for it in the right way, with the right tools, asking the right questions. And we have to be prepared for the answer to be strange, because at this point, after everything we've seen, strange is the only option that fits. Let me tell you about something happening in our own galaxy that might change how we think about what's possible in the universe, something that forces astronomers to question categories they thought were settled, to wonder if the catalogue of cosmic phenomena is far more incomplete than anyone imagined. Astronomers using the Australian Square Kilometre Array Pathfinder and NASA's Chandra X-ray Observatory discovered an object called ASKAP J18320911. It pulses like a heartbeat. Every 44 minutes, precisely, it emits a burst of radio waves that lasts about 2 minutes, then goes silent for 42 minutes, then bursts again. The cycle repeats with clockwork regularity. And here's what makes it uniquely strange. Chandra observations show X-ray pulses synchronized with those radio bursts. Not perfectly overlapping, but definitely correlated. This is the first object of its kind ever observed pulsing in both radio and X-rays with this kind of periodicity. The discovery came during a survey looking for transient radio sources, objects that appear and disappear or vary in brightness over time. Long-period transients, LPTs in the astronomical shorthand, are a relatively new category. Objects that flash in radio wavelengths every tens of minutes to hours. They're rare, poorly understood. They don't fit neatly into any existing classification. We didn't know they existed until we had radio arrays capable of monitoring the sky continuously, with enough sensitivity to catch these slow, regular pulses. The data is precise. 2-minute burst, 42-minute silence, repeat, over and over. The object is localized to roughly 15,000 light-years away, somewhere in our galaxy, but not in any obvious stellar association or nebula. Just out there, in what appears to be relatively empty space, pulsing its mysterious signal into the cosmos. What could produce such a thing? The immediate suspects are all magnetically active objects. Magnetars, neutron stars with insanely powerful magnetic fields, are known to pulse. But magnetar pulses are usually much faster, milliseconds to seconds, not 44 minutes. You'd need some novel configuration, some reason for the magnetic field to store energy slowly and release it periodically, on timescales thousands of times longer than typical neutron star rotation. Nobody has a convincing model for that yet. The physics doesn't quite work with what we know about how magnetars behave. Ultramagnetized white dwarfs are another possibility. These are dead stellar cores that have collapsed down to roughly Earth's size, but still rotate and maintain strong magnetic fields. If you had a white dwarf spinning with a 44-minute period, which is unusually slow for these objects, and if it had active accretion or magnetic reconnection events synchronized to its rotation, you might get periodic pulses. But again, the timing is strange. Most white dwarfs either spin much faster, completing rotations in seconds or minutes, or have lost their magnetic fields entirely as they cool over billions of years. Binary systems offer another explanation. Two objects orbiting each other with a 44-minute period, some interaction between them producing periodic flares. Maybe accretion, material flowing from one star to another. Maybe tidal heating, gravitational forces flexing the objects and generating energy. But a 44-minute orbital period implies the objects are very close together, close enough that they should either have merged already or be spiraling inward rapidly due to gravitational wave emission. The system should be unstable on astronomical timescales. Yet there it is, pulsing away with perfect regularity. None of the standard models are satisfying. Each requires tweaking parameters, invoking special conditions, explaining away inconvenient observations. The pattern is there, undeniable in the data, but the explanation remains elusive. And this is before we even try to connect it to 3I Atlas, which seems impossible on the surface. ASKP J1832 is a galactic object, probably stellar in nature, pulsing in radio and X-rays. 3I Atlas is an interstellar visitor showing optical and infrared anomalies with no confirmed radio or X-ray detections. They're completely different types of phenomena in completely different contexts, separated by scales of distance and energy that make any connection seem absurd. But here's why I'm bringing this up. Here's why these two mysteries might belong in the same conversation, even if they're not directly related. If one object in our galaxy can break all the existing patterns, can produce a signal that doesn't match any known class of astronomical object, then we should be humble about declaring what is and isn't possible for other weird objects we encounter. ASKAP J1832 is proof that the universe still has tricks we haven't catalogued, mechanisms we don't understand, classes of objects we haven't discovered yet. The discovery also highlights how much we miss. ASKAP is a relatively new radio telescope array, only operational for a few years. Chandra has been orbiting since 1999, but it can only observe what we point it at, and telescope time is precious, allocated through competitive proposals. ASKAP J1832 has probably been pulsing for thousands or millions of years, and we only just noticed. How many other strange objects are out there, detectable with current technology, but not yet found because we haven't looked in the right place or the right way? This changes the context for thinking about 3I Atlas. Before ASKAP J1832, you might have said that weird periodic signals in multiple wavelength bands aren't something natural objects do. So any claim of such signals is probably instrumental error or misinterpretation. Now we know such signals exist, we have proof, and we have no complete explanation for them. That should make us more cautious about dismissing anomalies in other objects just because they don't fit existing models. Could there be any connection between these phenomena? Any shared physics operating in different contexts? It sounds absurd when you first consider it. One is a galactic object at stellar mass scales. The other is a small icy body from another star system. They operate in completely different energy regimes. But let's explore the question anyway, because sometimes the wildest seeming connections reveal unexpected truths about how nature works. Start with energy scales. ASKAP J1832 produces radio and X-ray pulses. Radio emission can come from synchrotron radiation, charged particles spiraling in magnetic fields, or from coherent plasma processes, where organized motions of electrons generate electromagnetic waves. X-rays require higher energies, hot plasma at millions of degrees, magnetic reconnection events, particle acceleration to relativistic speeds. These are energetic processes, far more energetic than anything we associate with comets, which are just ice and rock heated by sunlight. But what if 3I/Atlas is carrying or generating magnetic fields? Comets do have induced magnetospheres. When the solar wind, that stream of charged particles constantly flowing from the sun, interacts with a comet's ionized coma, the interaction creates magnetic field structures. They're weak compared to planetary magnetospheres or stellar fields, but they exist. If 3I/Atlas had an unusually strong internal field, or if it was carrying charged particles that created field structures beyond what we normally see, could those fields produce detectable radio emission under the right conditions? Plasma physics gives us some possibilities. Coherent radio emission can come from plasma instabilities, from regions where the density of charged particles varies sharply, from boundary layers where different plasmas interact. If 3I Atlas is venting gas, that gas gets ionized by solar ultraviolet light. An ionized coma is a plasma, and plasmas can support waves, instabilities, emission mechanisms. Most of the time these are too weak to detect, but under special conditions, maybe extreme charge densities or unusual magnetic configurations, you might get detectable signals. The timing is completely different though. ASKAP J1832 pulses every 44 minutes with precise regularity. That regularity suggests rotation, orbital motion, or some kind of resonant oscillation, a physical cycle that repeats because of the object's structure or configuration. 3I Atlas doesn't show that kind of periodicity in its optical observations. If there's periodic behavior, it's on different timescales, days or weeks rather than minutes, so any shared mechanism would have to operate across a huge range of characteristic times, which seems unlikely, unless there's some underlying process that scales differently in different environments. What about X-rays? X-ray emission from comets has been detected before. It's produced when solar wind ions undergo charge exchange with neutral atoms in the coma. A solar wind ion, stripped of electrons by conditions in the sun's corona, encounters a neutral atom in the comet's atmosphere. The ion captures an electron from the neutral atom, dropping into an excited state, then releases that energy as an X-ray photon. It's faint, requires sensitive instruments to detect, but it's real. Multiple comets have shown this emission when observed with X-ray telescopes. If 3I Atlas has an unusually dense or active coma, X-ray emission wouldn't be surprising. The question is whether that emission would be periodic, structured, synchronized with anything else we're observing. Natural charge exchange is pretty uniform, not pulsed. You'd expect a steady glow rather than bursts. Unless something about the coma structure or the solar-wind interaction creates time-varying conditions. Let me offer a speculative hypothesis, just as a thought experiment. Suppose there's a class of objects, natural or otherwise, that maintain strong, localized magnetic fields and dense plasma environments. In a galactic context with stellar mass scales and compact objects like neutron stars or white dwarfs, you get something like ASKAP J1832, regular pulses from rotation or oscillation, radio and X-ray emission from plasma processes operating in strong magnetic fields. In an interstellar context, with a much smaller object like 3I Atlas, the same underlying field and plasma physics operates, but manifests differently. Confined comas, unusual gas-to-dust ratios, maybe radio bursts too faint or brief to have been detected yet in the limited observations we've made. This hypothesis makes testable predictions. If 3I Atlas and ASKAP J1832 share underlying physics, we should look for faint radio pulses from 3I Atlas, especially during perihelion, when solar-wind interaction is strongest. X-ray flashes correlated with optical brightening or gas production events. Polarization signatures in scattered light that indicate organized magnetic fields. Radio observations of background sources seen through the coma might show Faraday rotation, a twisting of polarization that reveals magnetic field strength. Most of these observations haven't been done or reported. Radio telescopes haven't been systematically monitoring 3I Atlas at high time resolution. X-ray observatories might not have been pointed at it during active phases. The data to confirm or rule out the connection might simply not exist yet. But the framework for testing is clear. The observations are possible with current instruments. The question is whether anyone will dedicate the telescope time and resources to look. The comparison is useful even if the answer turns out negative. If we observe 3I Atlas at radio wavelengths during its next active period and see nothing, that constrains models. It tells us there's no coherent plasma emission, no synchrotron radiation, no radio-producing mechanism operating. That's valuable information. It eliminates hypotheses, and if we do find radio pulses or X-ray correlations, or any of the signatures we're predicting, that would be extraordinary. It would suggest 3I Atlas is doing something far outside the normal behavior of comets, something that connects it to active stellar objects. That would push us firmly into exotic territory, where conventional explanations no longer hold. Now let me tell you about a single particle that changed how we think about cosmic violence. Deep beneath the Mediterranean Sea, an array of detectors called KM3net recorded something that shouldn't exist according to our comfortable understanding of particle physics and cosmic ray acceleration. A neutrino with an energy of 220 peta-electron volts slammed through the detector, leaving a trail of light that told a story about the most extreme processes in the universe. Let me give you a sense of scale, because numbers this large lose their intuitive weight. A peta-electron volt is 1,000,000 billion electron volts. The Large Hadron Collider, the most powerful particle accelerator humans have ever built, accelerates protons to about 14 trillion electron volts. Enormous energies by human standards, energies that probe the fundamental structure of matter. This neutrino was carrying 16,000 times more energy than those protons. It's a cosmic bullet fired by something so powerful we don't have a complete theory for how it works. Neutrinos are ghost particles. They pass through normal matter as if it isn't there. Right now, as you listen to these words, billions of neutrinos from the sun are streaming through your body, through the device you're using, through the Earth itself, continuing into space without interacting with a single atom. They have almost no mass, no electric charge, no properties that would let them bump into ordinary matter in the ways that photons or electrons or protons do. Detecting them requires enormous volumes of transparent material, ice or water, instrumented with sensors that watch for the rare occasions when a neutrino does interact. When it strikes an atomic nucleus just right, it produces a charged particle that moves through the medium faster than light can travel in that medium. This creates Cherenkov radiation, a cone of light similar to a sonic boom, but in electromagnetic radiation. By detecting that flash of blue light and tracking its pattern, you can work backward to determine the neutrino's energy and direction. KM3net operates in the Mediterranean, using the sea itself as the detector volume. Arrays of light sensors hang on cables, monitoring cubic kilometers of water for the telltale flash. The ARCA component detected this particular event, saw the characteristic pattern of a muon track, worked backward through the physics to determine the neutrino must have had at least 220 peta-electron volts of energy. The analysis has been confirmed. Multiple checks, different reconstruction algorithms. This isn't a glitch or misidentification. It's real. Why does this matter beyond just being an impressive number? Because neutrinos at these energies point to cosmic accelerators operating at scales we barely understand. The most powerful candidates are blazars, supermassive black holes at the centers of galaxies that are actively feeding. As matter spirals into these black holes, not all of it falls in. Some gets channeled into jets, narrow beams of plasma launched at nearly the speed of light. Those jets can accelerate protons to enormous energies. When those protons collide with ambient photons or matter, they produce particles called pions. And when pions decay, they create neutrinos. Gamma-ray bursts are another possibility. The death screams of massive stars collapsing into black holes. For a few seconds or minutes, these events shine brighter than entire galaxies, releasing more energy than the Sun will produce in its entire lifetime. Anything that can accelerate particles to the energies this neutrino carried is operating at the extremes of physics, in conditions we can barely simulate even in theory. Now here's where this connects to our story, tenuously but worth exploring. Could 3I Atlas be embedded in, passing through, or somehow connected to a high-energy astrophysical environment? The object came from interstellar space. We know its rough trajectory. We can trace it back into the galaxy. But we don't know what it encountered on its journey. Did it pass through a supernova remnant, near a pulsar wind nebula, through regions of space where magnetic fields or plasma densities create particle acceleration zones? The speculation goes further, and I want to be clear this is speculation, not established science. If 3I Atlas is carrying exotic properties we haven't detected, fields or mechanisms we don't understand, could it interact with the solar wind or interplanetary medium in ways that produce high-energy particles? Could it somehow seed neutrino production through mechanisms that don't operate in normal comets? This sounds absurd until you remember that we don't actually know what 3I Atlas is. We're calling it a comet because it's in our solar system and shows some volatile activity, but everything about it is anomalous. The contradictions between observations, the missing tail, the gas without corresponding dust. If it's not a standard comet, if it's something else, then maybe its interactions with its environment produce signatures we haven't thought to look for. A concrete test exists. Neutrino detectors like KM3net, IceCube at the South Pole, and others maintain continuous monitoring. Their data is time-stamped with microsecond precision and direction resolved to within degrees. If a burst of high-energy neutrinos occurred coincident with 3I/Atlas's perihelion passage, with its active phases, with any unusual behavior we've observed optically or spectroscopically, that correlation would be significant. The chances of random coincidence are calculable. If the correlation is strong enough, it suggests a physical connection that demands explanation. This approach has worked before. When IceCube detected neutrinos from the direction of a known blazar during an active phase, it confirmed that blazars are indeed neutrino sources. Multi-messenger astronomy, the strategy of correlating signals across different types of particles and radiation, has revolutionized our understanding of extreme astrophysical events. Light travels at light speed. Neutrinos travel at essentially light speed, but aren't stopped by dust or gas. Gravitational waves travel at light speed, but are produced by different processes, mass accelerations, rather than electromagnetic interactions. Each messenger tells you something different about the source, because each is produced by different physics. Neutrinos are special in this multi-messenger toolkit because they're so hard to stop. If 3I Atlas is producing them, they'd escape directly from whatever process generates them, carrying information about energies and mechanisms that other forms of radiation might not reveal. They're the ultimate cosmic messenger for seeing into environments that are otherwise opaque. The 220 peta-electron-volt detection is proof that such messengers are out there, that we're living in a universe with processes violent and powerful enough to produce them. It's a reminder that our census of cosmic phenomena is incomplete. We don't know all the ways nature can accelerate particles, generate fields, produce high-energy radiation. New classes of objects, new mechanisms, are still being discovered as our instruments improve and our monitoring becomes more comprehensive. So when we look at 3I/Atlas with all its contradictions and anomalies, we should keep in mind that the universe has already shown us it can do things we didn't predict. ASKAP J1832 pulses in ways no model fully explains. A neutrino with unimaginable energy came from somewhere in the cosmos, produced by acceleration mechanisms at the edge of physical possibility. The catalogue of cosmic strangeness keeps growing. Maybe 3I/Atlas is just a comet with unusual composition, and we're overthinking the mystery. But maybe it's another entry in that catalogue, another phenomenon that will require new physics or new categories to explain. The only way to find out is to keep observing. Keep correlating different types of data. Keep asking whether different anomalies might be connected through physics we haven't fully mapped. And to do that effectively, we need access to all the data, including observations that might be sitting in archives, captured but not yet analyzed, including new observations we can still make if we coordinate efforts and prioritize these questions. So here's what needs to happen. Here's the path from mystery to answer, laid out in concrete steps that anyone with determination can pursue. First, we organize. This is too much work for scattered individuals. We need a citizen audit coalition, bringing together amateur astronomers who have telescope access, data scientists who can write code to search archives systematically, planetary scientists willing to contribute expertise, legal advocates who understand Freedom of Information Act processes, and programmers who can build tools for mining large data sets, distribute tasks, share findings, maintain transparency about methods and results, so everyone's work can be verified and built upon. The amateur astronomy community has proven remarkably capable in similar projects, discovering transiting exoplanets in Kepler data, classifying galaxy morphologies, monitoring variable stars, and detecting outbursts. The combination of distributed effort and varied expertise often catches things individual researchers miss. This wouldn't be the first time citizen scientists made crucial contributions to professional astronomy. Second, we calculate precise observation windows. Use publicly available ephemeris data to determine exactly when 3I/Atlas would have been within Psyche spacecraft's potential field of view. The JPL Horizons system provides this data. Calculate angular separations, visibility windows, favorable geometries accounting for spacecraft attitude constraints and operational modes. Identify specific dates and times when observations could have occurred, either deliberately or as part of routine monitoring. Third, we search existing archives systematically. NASA's planetary data system has standardized structures, but they're not always intuitive. Use automated scripts to search by instrument name, observation date ranges, target coordinates. Download metadata catalogs that contain summary information about observations. Use Python libraries that can parse PDS formats. Look not just for obvious matches, but for engineering data, calibration frames, observations marked as poor quality that might contain relevant data inadvertently. Fourth, if archive searches come up empty, we file formal Freedom of Information Act requests. Be specific. Request all raw image frames from Psyche's cameras during the calculated observation windows, along with metadata, instrument logs, data quality assessments. Specificity matters. Vague requests get vague responses or delays. Include the specific date ranges, instrument identifiers, coordinate fields. Make it easy for the response to be comprehensive. Fifth, we conduct the observational campaigns that can still be done. High-resolution polarimetry at multiple phase angles to reveal surface properties. Narrowband imaging during dormant phases to test whether activity continues when solar heating is minimal. Deep stacking with adaptive optics to push resolution limits. Coordinated multi-wavelength monitoring during the next active period. Radio and X-ray and optical simultaneously. These observations require telescope time allocations, coordination across facilities, but they're feasible with current instruments. This is a 90-day roadmap. Days 1 through 30. Organize the coalition and begin systematic work. Days 30 through 60. Compile results and prepare proposals. Days 60 through 90. Submit those proposals and follow up on information requests. It's concrete, achievable, using tools and procedures that exist right now. And here's where you come in. If you have data science skills, volunteer to help search archives and develop analysis tools. If you have access to telescopes, even small amateur instruments, contribute observations during coordinated campaigns. If you have legal expertise, assist with FOIA processes. If you have platforms or audiences, raise awareness about these questions and the importance of data transparency. If you want to support this kind of citizen science, there are ways to contribute resources that make the work possible. Every contribution accelerates the timeline from mystery to answer, because the data exists. Photons hit detectors, signals were recorded, bits are stored somewhere in archives, or will be collected in future observations. The question is whether we can access them, verify them, analyze them openly, and follow wherever they lead. Let me bring this home. What do we actually know for certain? TESS stacked over 9,000 frames and found no extended coma. That's solid, reproducible data. JWST detected gas emissions, carbon dioxide and water vapor, indicating volatile activity. Also solid. Ground-based telescopes reported varied results, some seeing asymmetries, others seeing little structure. The observations are real but inconsistent. Spacecraft observations from Psyche that might resolve contradictions haven't been publicly released, and we don't know definitively whether they exist. What remains ambiguous? The physical mechanism producing gas without obvious dust tail, the composition and structure of the nucleus, whether contradictions reflect genuinely anomalous behavior or just observational selection effects, whether electromagnetic or plasma processes play unusual roles, whether any multi-wavelength phenomena connect to 3I/Atlas. What is pure speculation? That it might be artificial or technological, that spacecraft data is being withheld for non-scientific reasons, that there's a pattern connecting different cosmic anomalies through exotic physics. These ideas are worth exploring, worth testing, but they're not supported by conclusive evidence yet. They're hypotheses, not facts. We're at a threshold. The easy path is calling it a weird comet and moving on. The harder path is acknowledging we don't understand it yet and committing to finding out why. Science progresses through exactly these moments. Most anomalies get explained within existing frameworks, but occasionally, rarely, they require fundamental rethinking. We don't know which kind of moment this is. The mystery is open. The tools are available. The tests are defined. Data exists, somewhere, in archives or instruments pointing at sky now. The question is whether we have collective will to pursue it, rigor to do it right, courage to accept whatever answers emerge. This is how discovery happens, not through sudden revelation, but through accumulated anomalies forcing questions. Investigations following those questions wherever they lead. Communities collaborating to turn observations into understanding. The 3-Eye Atlas mystery invites us into that process. It offers us a role in figuring out what's real and what's misinterpretation. The frontier is open, the mystery awaits, and somewhere in data we haven't seen yet, or in observations we haven't made yet, the answer is waiting to be found. If this mystery has pulled you in the way it's pulled me in, subscribe to Sleepy Science Drift. We're building a community that follows these questions seriously but peacefully, where curiosity doesn't demand belief, just attention, where the strange becomes a doorway, not a destination. Stay with us. The universe has more secrets to whisper, and we'll be here, listening carefully, watching the dark spaces between stars for the next visitor that refuses to make sense. Because that's where the truth lives, in the anomalies, in the contradictions, in the quiet spaces where reality bends just enough to show us we don't understand everything yet. And that's exactly where we want to be.